Hello everyone. Last time we have derived this dispersion relation for the extraordinary modes. So before analyzing this dispersion relation, I am going to talk about a few terms that are relevant in the discussion of these dispersion relations. Cutoff and resonance. Cutoff, by cutoff we means when the refractive index, which is C by V phi, or you can call it C k by omega, goes to 0. This is the condition for the cutoff. Ck by omega goes to 0, or n goes to 0, or you can say k goes to 0. And if k goes to 0, that means the wavelength is going to infinite. So this is the cutoff. Now for the resonance, this refractive index, which is Ck by omega, that goes to infinity. That means k also goes to infinity and lambda goes to 0. Now usually at cutoff, the wave is reflected back, and at resonance, wave is absorbed. Now we are going to analyze this dispersion relation for the corresponding cutoffs and resonance that occurs in the for these waves. So in order to analyze this, first I am going to simplify this relation. So I am going to simplify this relation. It's a simple algebra. And then we will reduce this dispersion relation in a way that we can analyze it for the cutoffs and resonances. Now as you can see that we have these kind of terms. Now here omega 4 minus omega square minus omega p square and this term. This all will give you omega square minus omega p square whole square minus omega square omega c square divided by now here you can see that I can write omega square minus omega p square minus omega c and omega square minus omega p square plus omega c divided by this term. Now here we have these two terms, this omega square minus omega p square minus omega c, and we have omega square minus omega p square plus omega c. So I'm going to solve one of these terms and then put up here the corresponding relation for this. First I'm going to solve this one. So let's take this term. which is omega square minus, I can write it omega c minus omega b square. So let's solve this one. So we have omega equals omega c plus minus omega c square plus 4 omega p square divided by 2. This is a simple quadratic formula for this kind of relations. Now here similarly for this term, I have minus omega c plus minus omega c square plus 4 omega p square by 2. Now I'm going to define two frequencies. One is omega L, which is minus omega c plus omega c square plus 4 omega p square by 2, and another omega r, which is omega c plus omega c square plus 4 omega p square by 2. From this relation, it is apparent that omega L is a lower frequency and omega R is a higher frequency. In a short while, I will tell you about this L and R, which is the left hand frequency and the right hand frequency. So if I want to convert these terms in the terms of omega L and omega R, so for this I will get omega minus omega L and omega R as its corresponding frequencies, and for this relation I will get, as you can see, if I take minus common, I will get minus omega c plus this term, so it will be minus omega R, and if I take the plus term, plus sign here, then I will get this omega. So I have these two terms. So these are the corresponding solution of these equations. So I can write, instead of this term, I can write omega plus omega L, omega minus omega R, and instead of this term I can write omega plus omega R and omega minus omega L. So you can see these are the roots of these equations. So now I have simplified this relation in terms of these values. Now here you can see that we have defined two terms, cutoffs and resonance. I'm writing it here. For cutoff we have k equals 0, and for resonance we have k infinity. So from here you can see that when omega equals omega r, we have this term equals to 0, means k equals 0, and when omega equals omega L, we have k equals 0. So for these ways, at omega equals omega r and at omega equals omega L, we have the cutoffs. And now you can see that when omega square equals omega p square plus omega c square, we will get an infinity here. So that will give us this term infinite, that's the resonance term. So at omega equals 0, also we have an infinity, and at omega equals omega h, we have an infinity. So there are two resonance terms. So now I am going to write the important, you can say, the frequencies in the dispersion of this wave. So I am okay. First, you can see we have when omega equals 0, we have I'm going to convert it back into omega square by c square k square. So I will write it in this way. So omega square by c square k square will be omega square minus omega h square omega plus omega L omega minus omega R omega plus omega R and omega minus omega L. Okay. Why I'm writing it in this form? Because we are going to plot this 1 over n square or omega square by c square k square with respect in terms of omega. We are going to plot, I will give you a plot in a short while. So we are going to plot this expression, which is basically v phi square over c square in terms of omega. So when omega equals 0, we have v phi square by c square equal 0. When omega equals omega h, we have v phi square over c square equals 0. When omega equals omega r, we have this quantity approaches to infinity. When omega equals omega r, 0, and this will give you infinity. Similarly, when omega equals omega L, we are going to again have an infinity. Now, keeping all these terms in mind, and there's something else I want to mention here, that what will happen between omega 0 and omega L. So we have this relation that omega L is less than omega h and is less than omega r. And we have another frequency, that is omega p. So we have this omega L less than omega p and omega h and less than omega r. So now I'm going to plot v phi square by c square versus the frequency by keeping in mind these values, and also I'm just give you an idea about what will happen in between these. So if we have a condition that we have omega greater than 0 but less than omega L, what will happen? So you can see when omega is between 0 and omega L, we have this term omega is less than omega L, so we have a negative from here. It is already less than omega R, so we have a negative from here, and we also going to have a negative from here. So negative, negative, and there is a positive. So we have another negative. So we have these negative terms here. So our v phi square over c square is going to be less than 0 for this range. Now when omega is going to be greater than omega L but it is less than omega p, we have greater than 0. That means that when omega is going to be greater than omega L, we have a positive here, but we have a negative here and here negative. So these two negatives will cancel out and we get overall a positive term. Now when omega is going to be greater than omega p but less than omega h, we again have this positive. But now there is a special condition that when omega is equals to omega p. Now you can see this relation from here. So when omega equals omega p, this term is going to be 0, and we have c squared by omega square equals 1, or omega square over c square equals 1. So at omega equals omega p, we are going to have v phi equals c. So that's one condition. And now I'm talking about omega greater than omega h but less than omega r. Now again you can see that if omega is less than omega r, we have a negative here, and it is greater than omega h, so we have a positive here. So there is a negative left over here. All other terms are going to give us a positive sign because omega r is greater than omega l, and these are all positive terms. We are going to have a negative here, and there will be a positive here. So our v phi square over c square is again going to be a negative. But when omega is greater than omega r, so we have v phi square over c square positive. Now keep in mind all these terms, that we have these zeros and infinities, and we have these relations. Now I'm going to plot this expression. Okay. So I am going to plot v phi square by c square versus omega. So we have defined certain frequencies, right? Omega L, omega P, omega H, and omega R. So I'm going to give certain name, omega L. Let's say this is omega P, and this is omega H, and this is going to be omega R. So as now you can see that for the frequency range omega greater than 0 and less than omega L, we have v phi square over c square negative. So we have a negative here. But at omega equals omega L, we have an infinity. And at omega equals omega r, we also have an infinity. But at omega equals omega h, we are going to have a 0 here. So as we have already defined that this is basically omega square by c square k square. So an infinity means we have a cutoff here. These are the two cutoffs, and this is the resonance. So when omega is going to be greater than omega L and less than omega P, this is positive. So basically this is positive, and it will decrease as we increase the value of omega. So this will drop like that. At omega equals omega h, we have a resonance. This v phi square over c square is going to be 0 at omega equals omega h. So we have a 0 here. What is the specialty of this omega p? That at omega equals omega p, this v phi is going to cut the value of 1. So at omega equals omega p, we have v phi equals c. After omega h, when omega is greater than omega h and less than omega r, we again have this v phi square over c square as a negative. So we have a negative here. And now I'm going to divide this. And then again, when omega is greater than omega r, this v phi is going to. There's another thing, that if we take omega approaches infinity, then v phi approaches c, or you can say v phi square by c square approaches the value of 1. So this is the graph of the X mode for V phi over C square, or you can say this is the inverse of the refractive index square. These are called non-propagation regions. These are non-propagation regions because, as I already mentioned, that V phi square over C square is going to be negative. As this is negative, so K is going to be imaginary, so there will be no propagation in these regions. So when an electromagnetic wave passes through regions where omega P and omega C are changing, so that they will encounter cutoffs and resonance. So this is the dispersion relation. This is the diagram for the refractive index square inverse versus omega.